Alright, so let's break down this thing into simple terms. Imagine you have like simple magical box called neural network. This box takes in some struct like numbers, then does some cool magic to turn them into other numbers. The goal is for the box to learn how to transform these numbers correctly so that you can give it new stuff. It can do great job guessing what comes out. So now if all layers inside the black box just did a simple straight line math, like adding or subtracting, then no matter how many layers there are, the whole thing will act on the straight line, right? So that's a kind of boring because it means you cannot solve complicated problem with that. So think of it like trying to draw a picture with only straight lines. So you'd never get anything simple, but simple shapes, like, right? So that's why we need something special inside the magic box called activation functions. So that adds some flexibility and complexity to the whole thing. So box can do something more than straight line magic. So these functions make each layer in the box smarter, like giving them different tools to work with. For example, one layer might be good at adding number, other layer might be good at multiplying numbers, third layer might be good at something new entirely. So without these special tools, non-linear activation functions, even if you add some layers to the box, it will be just like doing some kind of straight line math or an over again. So it's like having a bunch of identical blocks. You can stack them as you all want, and they're not going to help you build anything interesting. So non-linear activation functions are essential because they give each layer something unique to do, making the whole network much more powerful and capable of solving complex problems. So they add extra something to create the useful patterns and relationships through the data. So a neural network consists of layers of neurons that transform input data through mathematical operations represented by the weights and biases. So without wasting any more time, let's get into the fun part, right? So let's have our neural network, our basic thing where we try to visualize stuff. So this is our normal usual equation where we used to visualize the basic thing. So this thing can consist of all the activation functions, like it can be ReLU, it can be linear regression, it can be leaky ReLU, and all those which we have been through. And this will be our sigmoid function, and that's how it will be going to be working. So let's go through basic math. So g1 is going to be equals to w1 of x plus b1, then a1 is going to be equals to g1 of z1, right? But we can call it directly z1. So we can call this a1 equals to z1, which will be gz equals to z will be our linear activation function, right? So let's go on to new thing now. Z2 will be w2 a1 plus b2, then A true will be G true, Z true, and again Z true. Now we're going to write A1 here. Definition of A1 is going to be equals to Z1, which will be equal to W1x plus B1. And now the interesting part comes in. Definition of B2 equals to Z2, which equals to W2 A1. So we can replace A1 with this definition of A1 and we can get some results. So when we replace this definition of A1, we are going to get A2 equals to W2x plus B1. This will be our A1 plus B2. Right, now the interesting thing happens. So we can take this thing as a W2 plus W2 times x plus W2 B1 plus B2. Now this thing will be W1, this thing will be B1, and it will give us W1x plus B1 B dash, W dash and B dash, sorry, my bad. Then we're going to have this thing, and after that y is going to belong to this, and then unless you throw non-linear item there, you cannot compute more interesting function as you go deeper in the network. So there is just one place where you might use linear activation function gxz equals to z, and that's if you are doing machine learning on regression problems. So if y is real number, for example, if you're trying to predict housing prices, so y is not 0 and 1 but real number, anywhere from $0 of the price of house to up to however price house might get. Houses can potentially millions of dollars, right? So however much houses cost in dataset, if y takes on these real values, then it might be okay to have linear activation function, but so that your output y hat is a real number going to be anywhere from minus infinity to plus infinity. So the hidden units should not be using the activation functions, right? So they could use relu, they could use tan h, they could use leaky relu, but maybe something else. But so one place you might use linear activation function is usually the output layer. So other than that, using linear activation function in the hidden layer, except for some very special circumstances relating to compression that we are going to talk using linear activation function, is extremely rare. And of course, if we are going to predict housing prices, as you saw in the previous videos, because housing prices are all negative perhaps, even then you can use a value activation function so that your output y hats are going to be greater than equal to 0. I hope that gives you sense of why having non-linear activation function is critical part of it, developing neural networks. So that's all for this one. See you guys in the next video.